Sorry about that, guys. My Zoom client crashed. But I think we're back in business now. Okay. So today is your guys' day. It's our review day. I'd be happy to solve any problems that you guys have questions about, talk about any concepts, whatever you think will help you most on Monday's exam. Let's not waste any time. Flip over to the document camera here. Oh, today is the 30th. Okay. And what we'll be doing today is just review for exam 1. If you have questions about the structure of the exam, please refer back to the video from Monday. I spent the first 10 or 15 minutes of class on Monday outlining the structure and the sections that will be covered. So I'd like to focus today just on problem solving. So I see Hallie would like to see some trig derivatives, specifically sine and cosine. Please take a second, look through the homework in the study guide, and type any problem numbers you would like into the chat. If you want to see homework 1, problem 10, type HW1 /10 or whatever, something to let me know what you want to see and where it comes from. I'll give a few minutes for that, and then we'll get started. I'll begin with Hallie's question. So derivatives of sine and cosine are not bad. The derivative of sine x is cos x, and the derivative of cosine x is just the sine of x. Of course, there's all sorts of ways these can be glommed together, combined with polynomial functions and rational functions, other things. But this is the fundamental result. Okay. For your work on the study guide problems, just, you don't have to write down anything besides what you're using to solve the problems. If you're able to solve the problem without writing much down, then that's fine. I just want to see whatever it is you're writing down. So show me all of your process that you use to solve the problems. I'll take a look at that problem in particular to try and give some guidance. This is an answer to Daniel's question. So Daniel, on the first problem here, I'd like you to show me the limit laws. For example, in part A, we did something like this in class last time. I would say the limit as x goes to 2 of f of x plus g of x is equal to the limit as x goes to 2 of f of x plus the limit as x goes to 2 of g of x. And then you would just write in whatever those values are. You don't have to draw the graphs. I know what the graphs look like. I just want to see you applying the appropriate limit laws and then putting in the appropriate value for each limit. Okay, so Josh wants to see how to show something is differentiable. Daniel wants to look at the first question in the study. Oh no, yeah, just that question, okay. Jan wants to see the 15th problem from the study guide, and Daniel wants to see the second. So the second problem here is a squeeze theorem problem, and I would be happy to look at that. This is study guide 1, problem 2. And here they say if, and your numbers will be different, 8x is less than or equal to g of x is less than or equal to 4x to the 4 minus 4x squared plus 8, find the limit as x approaches 1 of g of x, and this is an 8 here. So I'll need to make a little more room so you guys can see everything. There we go. So the trick behind the second problem in the study guide is just to remember the squeeze theorem, which can be remembered very easily as saying limits obey inequalities. So I'd say remember
and I can give more examples to him.
So you can take the limit.
I haven't touched it once since I've been back.
It cannot be touched.
That's you gotta. I know that. You're talking to someone who knows that.
Let's be mindful of our classmates, and unless we're speaking to the class, make sure our mics are muted. So to attack the second problem of the study guide, whatever version of this you have, just take the limit as x approaches 1 everywhere. So according to that inequality, the limit as x approaches 1 of 8x is less than or equal to the limit as x approaches 1 of g of x is less than or equal to the limit as x approaches 1 in this polynomial, 4x to the 4 minus 4x squared plus 8. So if you have a compound inequality like this, you can take limits everywhere in that inequality. And then this is what we call the squeeze theorem or the policeman's theorem. So if this limit on the far left and this limit on the far right are both the same number, then the guy in the middle has no choice but to go to that number as well, right? If the policeman behind you is going to the police station and the policeman in front of you is going to the police station, your ass also going to the police station. So let's see what happens. Where is this guy going? Well, as x goes to 1, 8x goes to 8. The middle piece is the piece I'm trying to figure out. On the far right over here, as x goes to 1, this piece goes to 4 minus 4 plus 8. So therefore, by the squeeze theorem, the limit as x approaches 1 of g of x must exist and be equal to 8. So that's all that's intended there. And this problem is actually a gentle squeeze theorem problem in the sense that they gave you the inequality to begin with. Normally, I would give you the function g of x, and you would have to build this inequality. So you may want to look back at some of the problems in your homework that dealt with the squeeze theorem to make sure you are comfy building those inequalities. I'm going to do my best to go in an order that makes sense as far as problem difficulty and also respect the order in which you guys ask the questions. So let's take a quick look at 15 on the study guide and also 26 from homework 5. Okay, 15 from the study guide we can look at. This is similar to one we played with the other day. And then let me pull up homework 5. Number 26 there. And it's very similar in spirit. Okay. So 15 from the study guide is a little bit easier. And your numbers may vary, but here I have the limit as x goes to 0, sine 2x over 7x. And here what we want to do is recall that the limit as u goes to 0, sine u over u is 1. So this is, I want to make use of this fact somewhere. At the moment, this limit doesn't look exactly like this limit, but it looks kind of similar. Got the sine of some stuff over some other stuff. We're sending x to 0, and the top and bottom both go to 0 with x, so we need to be careful. If this was a 2 instead of a 7, then this limit would be 1. Because we could substitute u equals 2x and turn that limit into this limit. So that's my goal. I'd like to swap this 7 for a 2. And I can do that by multiplying by 2 over 2. This is the same as the sine of 2x over 14x times 2 over 1. Right, bringing the 2 from the denominator of the 2 over 2 into the function. And then I can pull the 7 out in the same fashion. So far, just algebra. Everybody able to follow these steps? Now in this piece, I can make a substitution. So I'm going to bring this up here, where I will let u be 2x. So the limit as x goes to 0, we note that u goes to 0 as x goes to 0. So this is the same as the limit as u goes to 0, sine of u over u, yeah, no 2 in here anymore because I substituted u equals 2x, times 2/7. And this piece is my special trig limit. It's 1.
I have a question.
Yes.
Is the formula provided, or we have to like memorize and know how to?
You need to know these. Yeah, no formula sheets, no, none of that.
Gotcha.
So the idea is I don't recommend doing things like flashcards. The trick is to work with them enough that you become familiar with them, right? When you're learning a new language, for example, you don't usually make flashcards of vocab words. Usually you practice forming sentences and speaking with people in that language until those things come naturally to you. Solving problems in mathematics is a lot like speaking with someone when learning a new language. So you just have to practice with these objects until they stay in your brain. If you do find yourself really struggling with that, the flashcard approach isn't the end of the world, but it's not what I would recommend. Either way though, you do need to know these things because they will not be provided for you on the test. Any questions on how we attack this problem? Okay, then I'm going to move to the similar homework problem, which is a slightly tougher version of this. It's 26, right? Yeah. Where we want to find the limit as x goes to 0 and the tangent of, t goes to 0. I'll use the variable x here, so I've already written it. Tangent of 10x over the sine of 2x. So it's the same sort of business. We're going to make use of that special trig limit, sine u over u, as u goes to 0. That limit is 1. And the only way I can do that is by breaking this up into pieces that look like that. So my first step here is going to look like writing tangent as sine over cosine. So I'll have limit x to 0, sine 10x over the cosine of 10x. That is the tangent of 10x. And then the 1 over sine of 2x, I'll write like this. So I need to introduce a 2x upstairs in this piece and a 10x downstairs in this piece. The cosine of 10x doesn't actually have any problems near 0. That piece is going to go to 1, so I'm going to peel him off, introduce the pieces I want. So this is going to be sine 10x over 10x times 2x over the sine of 2x times, I multiplied by 2x upstairs, so I need to multiply by 2x downstairs. I multiplied by 10x downstairs, so I need to multiply by 10x upstairs. And then my 1 over the cos of 10x is also still chilling. So it's just a matter of rearranging until I'm able to employ one of my special trig limits. The 10x over 2x, I can cancel the x's, and I just get 10 over 2, which is 5, and I can pop the 5 all the way out front. Then I have the limit as x goes to 0 in sine 10x over 10x, and here I'll make a little substitution, times the limit as x goes to 0. I'm going to write this as sine 2x over 2x to the negative first power. The 10 over 2 I've already sorted, that's out here. And then finally I have the limit as x goes to 0 and 1 over the cosine of 10x. This piece is not problematic, but these two pieces require a little bit of special treatment. Okay. So this piece is 1 over the cosine of 0. That's 1 over 1, which is 1. So I'm not worried about that piece. In this piece, I'm going to substitute u equals u equals 2x. And note that u goes to 0 as x goes to 0. In this piece, I'll substitute, I'm going to use a different variable because it means different things. W equals 10x. And note that w goes to 0 as x goes to 0. And then I will rewrite each of these pieces. So the 5 is just a 5. This piece becomes the limit as w goes to 0, sine w over w times. This piece becomes the limit as u goes to 0, sine u over u to the negative first. And then this last piece over here, this went to 1. So he has no bearing on the value of the limit. Finally, Sine w over w, as w goes to 0, that's 1. That's my special trig limit. Sine u over u, as u goes to 0, that's also 1. So this piece goes to 1 to the negative first power. And then the 1 on the end is just a 1. So 5 times 1 times 1 over 1 times 1 is 5. That's all. You may notice some patterns in these special trig limits. The limit came out to 5, 10 halves is 5. That can tell you what you're shooting for, but you still need to show your work. You need to justify that limit. You cannot just make that claim. Any questions on this procedure? Well, if I'm going to divide by 10x here, I need to multiply it here, right? Just like when you have a common denominator and you like multiply by 7 over 7 or whatever. Here I multiplied by 10x over 10x. I can't just shove it down here without putting it here. Right, yeah, I'm multiplying this expression by 1 in the ridiculous form 2x over 2x times 10x over 10x. And I do that so that I can rearrange like this. Yeah, that's exactly the idea. So I'm taking my fairly complicated expression here and introducing the pieces that I need in order to invoke my special trig limits that I know will go to 1. So I know sine 10x over 10x, that will go to 1. I know that 2x over sine 2x, or at least his reciprocal, would go to 1. So I need to get a 2x upstairs here, and I need to get a 10x downstairs here. And the only way I can do that is by also multiplying by a 10x up here and a 2x down here. Otherwise, these wouldn't be equal, right? So you guys in Calc 1, this is kind of the first rigorous class, or pseudo-rigorous class, where you want to be paying attention to your notation. We write equal signs between things if and only if they're equal. And in order for those to be equal, if I'm going to divide by 10x, I need to multiply by it. If I'm going to multiply by 2x, I need to also divide by it. And yeah, I knew to pull the cosine out to the side here because he's well behaved at 0. If I plug 0 in for x here, I don't get a 0 downstairs or any funny business like that. The cosine of 0 is 1. So I pulled him all the way to the side because he actually doesn't have any bearing on the limit. The value of cosine near 0 is 1. So I say, okay, I'm gonna pull him all the way out to the side. I know he doesn't actually change anything. The interesting part of the tangent function is the sine part. Does that make sense? Cool. Okay, so Josh wanted to see how we can prove a function to be differentiable or not. I've worked a few examples like this with you guys, but I have one that I'm kind of proud of from a problem set I put together for my pre-calc kids. Oh no, not office. Overleaf. Let me remind myself what it is we did here. AQ, working, something else projects. Space for canvas questions. Is this it? What have we joined these? This guy is neat. So, what was he coming from? He was coming from this. All right. So the function I have graphed there in red for you, I'm just going to take care of it from -2 to 4. I'll write this down and then we'll come back. Is 1/4 x squared if x is less than 0, and plain old x squared if x is greater than or equal to 0. So let's show, or say determine, whether f of x is differentiable
because I'm moving away and you run from me, so that makes me suspicious, so you'll bot.
at x equals 0. Same thing, unless we're talking, let's keep the mics muted, okay? Okay, I'm gonna do it. All right, so we wanted to see how to show whether a function is differentiable or not. So I have here this piecewise defined function, and I want to know whether it's differentiable at x equals 0. So I should set up the limit defining the derivative at 0 and see if the two one-sided limits agree with each other. F primed of 0 would be the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. So we look at the left and right limits separately. The limit as h goes to 0 from the left, f of 0 plus h minus f of 0 over h. F of 0 is defined by this piece. It's just 0 squared, which is 0. If I'm approaching 0 from the left, f of 0 plus h is a little bit smaller than 0. So that would mean I'm using this piece. So this is the limit as h goes to 0 from the left, 1/4 h squared minus 0 over h. Which is 1/4 limit h to 0 from the left, h squared over h. And you can cancel an h. You get 1/4 lim h to 0 from the left of h. So this guy is 1/4 times 0, which is 0. So in other words, if you're looking at this graph, the tangent line as you approach 0 is going towards having slope 0. And the question is, does it do the same thing from the other side? So we've calculated the limit that would define f primed of 0 from the left. We found that that limit is 0. What about from the right? This would be the limit as h goes to 0 from the right. Here I'm considering h as being a little bit bigger than 0. So 0 plus h is bigger than 0. So I'm using this definition. F of 0 is still 0. So the limit as h goes to 0 from the right is just of h squared over h. There's no 1/4. And again, you can cancel. And again, you get 0. So that function is differentiable. Therefore, f primed of 0 equal lim h to 0 f of 0 plus h minus f of 0 over h. The overall limit that defines the derivative does exist. And and it equals 0. So the function is differentiable at 0. I'll abbreviate differentiable as diffable. And f primed of 0 is 0. So this function is differentiable at 0. And always the way you check is first, remember you check differentiability one point at a time. So you write down the limit that defines the derivative for that point. Then you investigate the left and right limits separately. If those left and right limits, which define the derivative, both exist and are equal to one another, then the overall limit that defines the derivative does exist. And that means the function is differentiable at that point. And what's more, you get the value of the derivative out for free. What does this look like if your function is not differentiable? So I'll stay here for just a second. Any questions on this procedure? Let's see, maybe my chat notifications aren't working. Let's see. Yeah, we'll do those next. But any questions on this? Josh, you feel good about this?
How did you pull the 1/4 out in front?
Because 1/4 h squared minus 0 is just 1/4 h squared. So 1/4 is a factor of this whole thing. And since it's a constant, it can come out front. So I'm using here the limit rule that says limit of a constant times some function is the same as the constant times the limit of that function. So here c is 1/4, and my function is really of the variable h, not x, but the same rule works, right? So this is 1/4 h squared over h. The 1/4 is thus a constant multiple and can come out front. You could have left it in and everything would have gone the same. Where did I get the h squared? Well, what is f of 0 plus h? It depends on whether h is positive or negative. If h is positive, then 0 plus h is positive, which means I'm looking at an input for x, which is greater than 0. So I would use this guy. So in the limit as h goes to 0 from the right, 0 plus h is positive. So f of 0 plus h is 0 plus h squared, following this part of the piecewise function. And in the limit as h goes to 0 from the left, 0 plus h is negative, because h is a little bit smaller than 0. So f of 0 plus h would be 1/4 0 plus h all squared, which is just 1/4 h squared. So the h squareds came from these guys. Making sense? These differentiability questions are really only fun for piecewise functions. There are some non-piecewise functions that I could give you questions like this about, but they're actually quite hard to work with. Things like x squared times the sine of 1 over x, that sort of shit. Much harder to work with. So when I give questions like these at this level in Calc 1, this is the appropriate way to do it. If this was a graduate class, I would hit you with some harder stuff. But for now, this is really the only way we can do it. Now that function I had graphed for you on in the overleaf using ticks, it looked like it should be differentiable at 0, doesn't it? This looks like a smooth connection down here. Definitely not differentiable here because we're not even continuous there. But what about up here? This doesn't look smooth, does it? So I would hypothesize that this function is not differentiable at x equals 2, even though it is continuous there. And I think it would be a good exercise to run through that. So allow me to do that quickly. And then what would that be? That's slope -1, so we draw 5. So this would be 6 minus x if x is greater than 2. So let's ask whether this f of x is diffable at x equals 2. Same sort of question. This is a 6 minus x down here. And I'll do 12 from homework 5, then 14 from the study guide after this. So here, I need to look into what should be f primed of 2, which is the limit as h goes to 0, f of 2 plus h minus f of 2 over h. You see how the value where we're checking differentiability figures into the formula. F of 2 I know. F of 2 plus h is going to depend on whether we're going from the left or the right, but f of 2 itself is defined always to be 2 squared, which is 4. So again, the one-sided limits are the limit as h approaches 0 from the left, f of 2 plus h minus 4 over h. If h is approaching 0 from the left, is 2 plus h larger or smaller than 2? I'll repeat the question just in case you didn't hear. As h approaches 0 from the left, is 2 plus h
It's a little smaller than 2.
larger or smaller than 2? Yeah, h going to 0 from the left means I'm imagining small negative numbers for h, which means 2 plus h is a little bit smaller than 2, because if you add a small negative number to 2, that drags you left of 2. So f of 2 plus h is going to be defined by this part of the piecewise function. F of 2 plus h is 2 plus h quantity squared. And then I still have the minus 4 and the over h. So this is the left limit. I can FOIL out 2 plus h squared, and I get lim h to 0 minus 4 plus 4h plus h squared minus 4 over h. So I just FOILed this out. That's these three terms. And then the 4's will cancel. So the limit that would define the derivative when taken from the left is lim h 0 minus 4h plus h squared over h. You can factor in h and cancel with the downstairs. And you get 4 plus h. So this is tending to 4. On the other hand, the limit as h goes to 0 from the right, f of 2 plus h minus f of 2, which is 4, all over h. Since now h is going to 0 from the right, 2 plus h will be a little bit larger than 2, which means rather than using the x squared, I'm using the 6 plus x. So this is lim h to 0 plus 6 minus 2 plus h minus 4 over h, which is lim h to 0 plus 6 minus 2 minus h minus 4. Which is lim h to 0 plus 6 minus 2 is 4, 4 minus 4 is 0. You get negative h over h, cancel, cancel. And you have lim h to 0 plus of negative 1, which is negative 1. So I will stop here and ask you, is this function differentiable at 2?
No,
Why not? Correct. Why not?
because the limit from the left doesn't match the limit from the right.
Can you be just a little bit more specific? Nothing you've said is wrong, but it's not quite what we need. What limit? The limit of f of x?
The limit of x squared is not the same as the limit of 6 minus x.
So this is, I'm picking on you right now only because the language here is important and this is a common error. If you send x to 2 here and you send x to 2 here, they will be equal. They'll both be 4. But the limit that defines the derivative when taken from the left and the right aren't equal. So it's not f itself that we're taking the limit of, it's the difference quotient. So you're correct, and I believe that you have the right idea and everything is sound in your mind, but I want to be a little bit careful about how we write it. So I would conclude here saying f of x is not differentiable at x equals 2 because the limit which defines f primed of 2 does not exist because limit h to 0 f of 2 plus h minus f of 2 over h does not exist. You guys see the distinction there? It's a subtle and small distinction, but it's something that I encounter a lot. This is basically the difference between showing a function is differentiable and showing a function is continuous. This function is continuous at 2. You can see that from the graph. Or you could see that by taking the limit of this as x goes to 2 and taking the limit of this as x goes to 2, they agree. But the limit that defines the derivative, that limit does not exist because his left and right limits are different. So it's a tiny, tiny bit subtle. And I just want to make sure we all have this clear in our heads. To show that a function is or is not differentiable, you need to show whether or not the limit of the difference quotient, which defines the derivative, exists, not the limit of the function itself. Go ahead, Alex.
Oh, yeah, my question is, can you just do like the derivative of f of x entirely and you take the derivative of like both parts of the piecewise function? Would that be a way to show work without doing that much?
So yes and no. What you could do is differentiate each of these pieces on their own.
Yeah, exactly.
And then send x to 2 in that result. But what would that
would that be considered?
Not quite, because what you would show then is that the derivative function isn't continuous. And we don't know whether a differentiable function always has a continuous derivative. Do you see the difference? It's very, very subtle.
No, I don't see it. Can you explain it
Give
again?
me 1 second here. I don't want to burn too much more time on this, but here's the question. Yep. If f of x is differentiable at x equals a, must it be true that the derivative f primed of x is continuous at x equals a? So what you're talking about doing there, Alex, is taking the derivative of each piece of the piecewise function and showing that those derivative pieces don't match up. So what you would be
I mean, yeah, it's like a proof by contradiction, right?
well, only if you have the answer to this question. If the answer to this question is yes, then you would have an argument through contradiction. Is the answer to this question yes?
No.
Well, see, I wish this was an advanced calculus, a slightly higher level class. I could give you the most thorough answer to this question that exists, which is no, not necessarily, but something like that is true. Derivatives satisfy a condition called being Darboux. They're not necessarily continuous, but derivatives are Darboux, D-A-R-B-O-U-X, if you want to Google it. It means they satisfy the intermediate value property. So if you have a function that must be the derivative of your function, and that function does not satisfy the intermediate value property at A, then you could conclude that the original function isn't differentiable at A. But the purpose of us doing these problems is not that. It is to make sure that you guys understand what it means for a function to be differentiable. And that, for us, is saying that this limit exists. And the most direct way to check that is what we're doing here. So I do want you to practice this skill. I know it's very possible to get through the homework without ever doing this. And it is also very possible that I will have a question on the test that asks you to do this. I think I've warned you of that a few times. So this skill of checking differentiability by checking whether the limit of the difference quotient at that x value does or does not exist is a necessary skill. And having gone through it once or twice, you'll start to build the type of intuition that leads to good answers to the question that Alex was asking. If you look over here, the derivative of this function, the slope of the tangent line, as you approach 2 from the left, is certainly positive. And the slope of the tangent line as you approach from the right is certainly negative. So if somehow this function were differentiable at this point, you would need a way for the derivative function to go from positive to negative, which would mean that the derivative would have to pass through 0. But because the derivative function does not exist here at 2, it's able to make a jump. And this is the connection between differentiability, continuity of the original function and its derivative that I want you guys to be thinking about. So I really do want you to at least once go through this procedure blind on your own and make sure you're comfortable with it, and then try to think about what it is that you're showing there. All right, this is certainly enough time on one problem. Any questions about any of the technical steps here? Okay, then I think question 12 from homework 5 and 14 from the study guide are next. This is 5, right? Yeah, number 12. I like this problem a lot. This is a good problem. Let's take a look. So again, here the answer is no, but derivatives are Darboux. You don't need to know that, but if you're curious, you're welcome to Google it. If you take advanced calculus or real analysis later in your careers, you will prove that. For number 12 on homework 5, they give us the graph of f and g. They tell us that u is f times g and v is f over g. So I'll write that down. Okay. They want us to find u primed of 1 and v primed of 5. So in order to find u primed of 1, I need to know what u primed of x is. That means I need to differentiate this expression. Similarly, in order to find v primed of 5, I need to know what v primed of x is. So I need to differentiate this expression. Let's go after the u's first. U primed of x is what you get when you differentiate u of x. So that's what you get when you differentiate f times g. This requires the product rule. This is f primed of x times g of x plus f of x times g primed of x. My cat is clawing at the door, so I'm going to let him in. Oh, it's not. No, bro. It's not. What are you doing, Victor? This ain't your room. What you doing? Okay. Not quite, Alyssa. If you just multiplied the slopes of f of 1 and g of 1, that would be f primed of 1 times g primed of 1. So let's make a note here. That's a good question. U primed of 1 is not f primed of 1 times g primed of 1. Because u is the product of f and g. Doesn't imply that u primed is the product of f prime and g prime. In other words, we need to use the product rule here. All right, so no, it's a great question. I think everybody, that's their first intuition on this. And this problem's whole purpose is to kind of halt that runaway intuition. Intuition's a great thing, but you need to also always be sensitive to when it can lead you astray. And this is one of those places. So f primed of 1 is the slope of f at 1. G primed of 1 is the slope of g at 1. But if you multiply those, the result is not u primed of 1, because u primed follows from the product rule. But it will involve those things. So we'll take here, we can now go ahead and plug in 1. So u primed of 1 must be f primed of 1 times regular old g of 1 plus f of 1 times g primed of 1. So you'll take the slope of f times the y value of g plus the y value of f times the slope of g. See the distinction? It's a little bit subtle. So this is one of those cases where you want to sort of just trust the theorems, right? Trust the mathematics. The product rule will work. It'll never lead you wrong. So now we come back to our graph. F primed of 1, this first piece, is the slope of f at x equals 1. So here's my x-axis down here. Here's x equals 1. The slope of f there, well, what is this slope? Looks like the slope everywhere in here is 1, 2, 3, 4 over 1, 2 is 2, right? Yeah, the slope there is 2. So f primed of 1 is 2 times g of 1 is the y value on the graph of g there. That's just 1. Plus f of 1 is just the y value on the graph of f. That looks like it is 2 times g primed of 1 is the slope of g at 1, which is -1. So this looks like it's going to be 0. 2 times 1 plus 2 times -1, that's 2 minus 2, that's 0. So this is a nifty problem. Any questions on what I did to get u primed of 1 here? All right, we'll attack part B the same way, just using the quotient rule instead of the product rule. So v primed of x, we'll find that in general. That's the derivative of f of x over g of x. So f over g all primed. And now I use my quotient rule, low d high. That's g times f primed minus high d low, f times g primed all over low low, or g of x all squared. So when I've been doing these, I've been calling them schematics. This first line is kind of like a schematic. It's a setup. Similarly here, this is like the setup, and then we have to plug in. Well, for v, Jan, we have to use the quotient rule because v is the function v is defined to be f over g. And the only way we know to differentiate that now is with the quotient rule. And for u, I had to use the product rule because u is defined to be f times g. So there is no way to differentiate this guy with the product rule that we know yet. I'll actually show you a trick once you know the chain rule that will let you avoid ever using this in the future. But for now, this is all we have. The chain rule is a little bit complicated in some ways, and it's more applicable to what we'll be doing after exam 1. So now that we have our schematic, our plan, we can plug in 5, right? Because we wanted v primed of 5. So v primed of 5 is going to be g of 5 times f primed of 5 minus f of 5 times g primed of 5 all over g of 5 all squared. And into this, we can plug what we get from the graphs. So g of 5, let's see, where's 5 on this thing? These graphs are a little hard to read, right? 1, 2, 3, 4, 5, up to g. That looks like that's 1, 2. So g of 5 is 2 times f primed of 5 is the slope here. Looks like that's negative 1/3. Yeah, the slope here is definitely negative 1/3. We go down 1 over 1, 2, 3. And the slope there is constant everywhere throughout here. Minus f of 5, I lost 5. 1, 2, 3, 4, 5, here it is. F of 5 is 1, 2, 3. So that's minus 3 times g primed of 5. So what is the slope of g here? Well, it's the same slope everywhere through here. So what is this? We go 1, 2, 1, 2, 3. Looks like the slope there is 2/3. And then all of this is being divided by g of 5 quantity squared, that's 2 squared. So 2 times negative 1/3 is negative 2/3 minus 3 times positive 2/3. I'll leave it as the ratio over 3 because I want to combine those. So I'll call that 6/3. And everybody's getting divided by 4. Negative 2/3 minus 6/3 is negative 8/3 divided by 4. And that's the same as 8/3, negative 8/3, sorry, times 1/4. And it'll just fit here. That's a negative, let's see, 2/3. Because 8 by 4 is 2. So this again is a really good problem because it is a straightforward application of the 2 differentiation rules, product and quotient rule. No nasty calculations, you just have to show me that you understand the formulas and then you understand how to geometrically get the derivative as a slope. It's on this fellow. Okay, then let's keep moving. If everybody is comfy here, if you have questions, please ask them. That was 12 from homework 5. And I think there was another study guide question, right? Yeah, 14 from the study guide. So let's switch over to the study guide. This is a good one. Oh, where'd it go? It ran away from me. Yeah, this is a good one. There's some space here we can use. They told us f of theta is theta times sine theta times cos theta. This is a less straightforward application of the product rule. If I didn't have this theta here, then it would be a very straightforward application of the product rule. Sine theta times cos theta. So you differentiate sine, leave cosine alone. Then add that to what you get when you leave sine alone and differentiate cosine. But I've got this thing, which makes it more complicated. So what I would do is split this up into two pieces. The first piece I'll call U, and the second piece I'll call V. You could split it up however you wanted, but this is how I'm going to do it. So U is theta sine theta, and V is cos theta. And remember that U times V primed is U prime times V plus U times V primed. So here, f primed of theta should be theta sine theta primed times cos theta plus theta sine theta times cos theta primed. Okay. U prime times V plus U times V primed. This piece is not hard to deal with because I just have to differentiate cosine. But this piece is a little tricky because he on his own requires the product rule. So this is a product rule within a product rule. Again, I split as U and V. So that theta sine theta all primed, I'm going to put that in some parens here. U primed is 1 times V is sine theta plus U is theta times V primed is cos theta. And all of this is still being multiplied by the cos theta here. And then I've got this plus theta sine theta times the derivative of cosine, which is negative sine theta. So this is what we get. And now we can distribute combined like terms. But it's a little bit tricky. Let's distribute the cosine. I'll get cos theta sine theta. Plus theta cos theta is theta cos squared theta. And then here I have theta sine theta times negative sine theta, that's minus theta sine squared theta.
Then again, we could just extend like the product rule to like 3 different multiplications.
Yeah, in fact, there's a simple-ish way to extend the product rule to n product terms. But for our purposes, I think it's best, so a mathematician is happy when they can break a problem that is complicated down into problems they previously know how to solve. So by breaking this guy down into 2 steps of the product rule, each one we know how to do, we're able to attack this in a way that we know. So again, this would be my suggestion. Just remember the product rule. And at each step where you need to differentiate a product, pick one piece to call U and another piece to call V. And then apply the product rule. Sure, you have to do 2 different steps. Okay, but that's at least a path to a solution. That's something that will get you where you need to go. If you want to see the generalized product rule, that's called the Leibniz rule. So I'm going to conclude this here and say note. Yes, you can extend the product rule to 3 things like U times V times W, all primed, is U primed times V times W plus U times V primed times W. Let's see, so if I did just this, that would be that. And then I would tack on, let's see, so that's treating the U times V as our first part, W comes along for the ride. Actually, let me not do this. I don't think this is going to help. The generalized product rule says if you have a product of n functions that you want to differentiate, it looks actually an awful lot like the binomial theorem. Where k here stands for the kth derivative. But I don't think you want to think of it like this. This is a mess, yeah? I think what you do—
I mean, I just think about it as the
break these down.
combinations of one derivative multiplied by the other functions.
That's what they
You
are.
just
Yep.
like swap, yeah.
Yeah, that's exactly what this is. And the number of combinations you get here is what's counted by that binomial coefficient. But for our purposes in this class, I just want to make sure that you guys can take the derivatives of the sort of functions you're going to bump into in physics, in chemistry, in your other math classes. And for that, it is sufficient to chip away one product rule at a time. If you want the general thing here, this is called Leibniz rule. Leibniz generalized product rule.
Oh, now think of a generalized quotient rule.
It would follow from chain rule and the generalized product rule. But yeah, you could. Derivatives of continued fractions or something like that could be calculated.
Yeah.
Okay, I do want to stay focused here today on things that we need for our test. So what else would you guys like to see? I think we have a little bit of time left.
We're doing the test on Friday, right?
No, remember the school is closed on Friday. So the test is Monday.
Okay, and we would log in like Monday at the time class would start.
Mm-hmm.
And then we just do the test at that time.
Yep. Yeah,
Okay.
so I'm going to post an announcement to Canvas that looks a lot like the instructions for the study guide. I'll post an announcement that says instructions for exam 1. I'll be putting that up this weekend. Please read that very carefully before starting the test. But on Monday, what will happen is instead of coming to class, instead of clicking a Zoom link, you're going to log into our Canvas course at the time you would normally go to class. And then you'll go to assignments. There will be an assignment that says exam 1, take the test here. I'll show you. So I went through this recently for my pre-calc class. You'll see 2 assignments related to exam 1. One will say take the test here. One will say written work, submit the scans of your work here. So at 12:30 on Monday, you're going to sign into our class and click on what looks like this. That will take you to this, which will look for you guys just like this. You'll launch the proctoring. If you haven't already installed HonorLock, it will install HonorLock for you. You will need to have your ID and a webcam. Once you've gone through the identity verification process with HonorLock, you'll be taken to the test. The test is in Canvas. For the true, false, and multiple choice questions, you just pick the correct answer. For the free response questions, you need to write down all of your work, just like you would on a written test in class, showing every single step. You'll type only your final answer in the box for the free response questions. And then once you complete the test, you'll come back to assignments and you'll click on this guy, submit your scans. You will take your cell phone or your scanner or whatever you use to scan documents, scan your written work for the free response questions, and upload them there. It will only accept PDFs. So you need to make sure you're comfy with using Cam Scanner and getting a PDF, not just scanning it, but then saving the file somewhere that you can then upload it to Canvas. You can't go straight from Cam Scanner to Canvas. You have to save the file on your phone or on your laptop and then upload to Canvas. Any other kind of procedural questions about the test?
We could print, was there like a printout for a reference sheet?
No.
Oh, okay, I keep forgetting what a different class.
No formula sheets, no none of that. Yeah, you have to know this stuff. So the things that I would caution you on, the things that people forget, the limit definition of continuity, the limit definition of differentiability. We worked with that quite a bit today. The power rule, the rule for differentiating exponential functions, the product rule, and the quotient rule. Those are the main things that you're going to be tested on as far as calculation is concerned. You also need to be comfortable sketching the graph of a derivative given the graph of the original function, all that 2.8 stuff. Remember where you guessed the slope and then started drawing the graph of the derivative? You need to be comfortable using your limit laws. And really that's about it. You need to remember the derivatives of trig functions. But that topic, that list of topics that are covered on the exam, go back and check out the video from Monday where I went through and listed the topics and then also gave a few warnings about the particular things people forget. Jean, yeah, you can email me the study guide as soon as you finish it. Sooner the better. So as soon as you finish the study guide, scan it and send it to me. That way, one, you're getting practice using Cam Scanner and submitting things. And also the sooner you get it to me, the sooner I can get you feedback. I do have some bad news on this front. The college was kind enough to get me a Wacom drawing tablet so I can annotate your work and make comments just like I would if you handed it on paper. But this thing fucking sucks. I spent like 5 hours last night wrestling with this thing, trying to get it to give me decent output. It's not going as smoothly as I would like it to. So getting me the study guide as soon as you can will increase the odds that I'm able to get you meaningful feedback before the day of the test. So try to do that. Any other questions before we head out, guys? Of course, you're welcome.
We don't need to email the study guide, do we?
Don't email it. No, submit it
okay.
in Canvas, right? Submit in Canvas. So the study guide.
Oh, we do have to?
Yeah. So make sure you read the announcements, right? There's an announcement there that says, you know, instructions for study guide 1. You need to come into Canvas here, go to assignments. There's a place to upload study guide 1. This is what your 25 points comes from. Doesn't come from the WebAssign score. The WebAssign thing
I thought it did.
is homework. So you gotta upload your written work for the study guide. If you're uncertain, please always come in and read the announcements.
Yikes. Okay.
I'm glad you asked. No, it's okay. Glad you asked. All righty, then. I got to get running, guys. I got another class. If you want to chat more, I have an office hour this afternoon, normal time for Mondays and Wednesdays, 3:30 to 4:30. And otherwise, that is it. Come talk to me during any of my office hours between now and the test. If those don't work, you can schedule an extra one. But yeah, otherwise, I will see you guys next time on Wednesday of next week after you take the test.
Oh yeah, Mister, for that sum of reciprocal primes, I think I could go somewhere, but I'm not sure. Because you know that you have the infinite product of like 1 minus 1 over p to like the -2, right? You
Mhm.
could think of that as a geometric series.
Yes, you
Like
can. Yeah, and that's a common trick there, but that's zeta of 2. That's not the prime sum.
Oh, well, yeah, exactly. But I
Remember,
mean,
that's,
I don't know. I mean, could you get somewhere with that?
well, so
Think
expanding,
about it that way.
right, this has nothing to do with calculus. So if you guys don't need to stress about this. Yeah, this is true. And then this object, you can expand this as a power series geometrically. And that's a common trick. You'll be looking at what's called a hypergeometric series there. But the result is zeta of 2, not the zeta prime function of 2.
Right.
I can't draw zeta right now.
I also took the log, and then that breaks into 2 infinite sums. Can I get rid of the other infinite sum outside somehow?
I don't know. Give it a shot. Give it a shot. Write it up. Send it to me. I'll let you know if it's kosher. I did get a response back from Krishna Alati, and he said he would be very excited to talk with you, and he thanked me for contacting him on your behalf. Did he send you anything?
I haven't checked, but he probably did.
Yeah, have a look at your email. Krishna sent back to me, "Dear John, good to hear from you. Thanks for drawing our attention regarding this bright student interested in analytic number theory. Best wishes, Krishna." So, yeah, he would be
No,
a
I don't think I got an email yet.
contact there. If you haven't got an email from him, feel free to hit him up. Remember, his email is alladik@ufl.edu, and he is excited to hear from you. But I got to get going. I got another class that starts in a few minutes, so it's great to see you guys. If you have any questions, you want to see me in office hours, please do. If the office hours don't work for you, email me to set up an alternate time, because I don't want anybody coming into this test without having had an opportunity to talk. All right, I got to go. I'll see you guys later.